Chapter 1: Relations and Relation Schemes. This chapter introduces the fundamental principles of the relational model, a structured way of viewing data that forms the basis of most modern databases. The core idea of this model is its uniformity. All data is stored in two-dimensional tables, which are formally called relations. Each row within a relation is called a tuple. A tuple represents a single object or a relationship from the real world, such as a specific flight or an employee's record. All tuples within the same relation follow an identical format. This format is defined by a set of columns, each of which is an attribute that describes a particular characteristic. For instance, a relation for flights might have attributes for flight number, origin, destination, and departure time. Every attribute is associated with a domain, which is simply the set of all valid values that can appear in that column. The set of all attribute names for a particular relation defines its relation scheme. A critical concept for ensuring data integrity is the key. A key is one or more attributes whose combined values uniquely identify each tuple in a relation. For example, a flight number would be a key because no two flights share the same number. A key must be minimal, meaning no attribute can be removed from it while still maintaining the uniqueness property. Any set of attributes that contains a key is known as a superkey. Finally, the chapter establishes that while the data itself is dynamic, tuples can be added, deleted, or changed, the underlying structure or scheme is considered fixed. The database system enforces this structure by rejecting any update that would violate the rules, such as creating a duplicate key or inserting a value that is outside an attribute's defined domain. Chapter 2: Relational Operators. This chapter details the fundamental operations or operators that are used to manipulate entire relations. These operators are the building blocks of relational algebra, a formal system for retrieving and combining data. The main operators covered are Boolean operations. Because relations with the same structure are essentially sets of rows, the standard set operations of union, intersection, and difference can be applied to them. The chapter also describes the active complement, which is a practical version of the set complement that is guaranteed to produce a finite result. Select, sigma. This operation acts as a filter, creating a new relation by choosing only the rows, tuples, from an existing relation that satisfy a given condition. For instance, it could select all flights departing from JFK. A key property of the select operator is that it is commutative, meaning the order of multiple selections does not change the final outcome. Project, pi. This operation creates a new relation by selecting a subset of columns, attributes, from an existing relation. After the columns are chosen, any resulting duplicate rows are automatically eliminated to maintain the set-based nature of relations. Join, delta. This is one of the most powerful operators used to combine information from two different relations. It works by matching tuples based on the values in their common attributes. A new, wider tuple is formed for every pair of tuples from the input relations that have the same values on all shared attributes. If the relations have no attributes in common, the join operation becomes a Cartesian product. The join is both commutative and associative, so the order of joining multiple tables does not affect the result. A crucial conclusion from this chapter is that these operators are composable, allowing for the creation of sophisticated queries. The concept of a lossless decomposition is also introduced, describing the ideal situation where a relation can be broken down using projections and then perfectly reconstructed using joins, a cornerstone of good database design. Chapter 3: More Operations on Relations. This chapter builds upon the foundational operators from the previous chapter by introducing a set of more advanced and specialized operators. Together, these tools form a complete system known as relational algebra, which provides a full-featured procedural way to query data. The advanced operators presented include divide. This is a complex operator designed to answer for all types of questions. For example, if you had a list of pilots and the aircraft they can fly, you could use the divide operator to find which pilots are certified to fly all of the aircraft in a specific required set. Renaming, delta. This operator changes the name of an attribute. While seemingly simple, it is essential for certain queries, particularly those that require joining a relation with a copy of itself. Renaming allows the system to distinguish between the same attribute from different instances of the relation in the join. Equijoin. This is a specific type of join that combines two relations based on columns that have different names but contain values from the same domain. For example, one could join a flights table on its destination city attribute with a hotels table on its location attribute. The joining columns are repeated in the result. Theta join. This is the most general version of the join. Instead of being restricted to equality, it allows relations to be combined based on any comparison condition, such as less than or greater than. A classic example is finding all flight connections where the arrival time of the first flight is earlier than the departure time of the second. The chapter concludes that the full set of relational algebra operators is logically redundant. A much smaller core set, select, project, union, difference, join, and rename, is sufficient to express any query that the full algebra can. The chapter also briefly mentions other useful but non-standard operators like split and factor, which are not part of the formal algebra because they do not produce a single relation as their output. Chapter 4. Functional Dependencies. This chapter introduces the concept of functional dependencies, FDs, which are rules or constraints that describe the relationships between attributes within a single relation. FDs are a cornerstone of relational database design theory. A functional dependency, which is written as X to Y, states that the values of the attributes in set X uniquely determine the values of the attributes in set Y. This means that if you take any two rows from a relation and they have the same values for all the attributes in X, they are guaranteed to also have the same values for all the attributes in Y. This idea is a direct generalization of the concept of a key. If a set of attributes K is a key for a relation, then by definition, it uniquely determines all other attributes in that relation. This can be formally expressed with the functional dependency K to R, where R is the set of all attributes in the relation. Understanding and identifying the functional dependencies in a dataset is the first and most critical step in designing a database that is efficient and free from logical inconsistencies and update problems. Chapter 5. Covers for functional dependencies. This chapter focuses on methods for managing and simplifying sets of functional dependencies. Since a database can be governed by a large number of FDs, it's crucial to find a more concise representation. This is achieved by finding a cover, which is a smaller set of FDs that is logically equivalent to the original set. The key concepts explored are equivalent sets and closures. Two sets of FDs are equivalent if they logically imply the exact set of dependencies. The complete set of all FDs that can be inferred from a given set is known as its closure. Non-redundant cover. A cover is non-redundant if it contains no superfluous FDs. In other words, every FD in the set is essential, and removing any one of them would reduce the set's logical power. An algorithm is presented to find a non-redundant cover by systematically checking and removing any FD that can be derived from the others in the set. Reduced cover and extraneous attributes. A cover can be further simplified by removing extraneous attributes. An attribute is extraneous if it can be removed from either the left or right side of an FD without changing the overall set of implied dependencies. A reduced cover has no redundant FDs and no extraneous attributes. Canonical cover. This is the most simplified form. A canonical cover is a reduced cover where every FD has only a single attribute on its right-hand side. Any set of FDs can be converted into an equivalent canonical cover. In conclusion, this chapter provides the theoretical tools and algorithms needed to distill any collection of FDs into a minimal, efficient representation. Using a canonical cover instead of the original, larger set simplifies the process of enforcing data integrity and is a key step in database design algorithms. Chapter 6: Databases and Normal Forms. This chapter applies the theory of functional dependencies, FDs, to the practical task of designing efficient and reliable relational databases. It introduces the concept of normalization, a systematic process for organizing attributes into relations to minimize data redundancy and prevent update anomalies, logical errors that can occur when adding, deleting, or modifying data. Normalization is achieved by ensuring that relations adhere to a series of progressively stricter rules called normal forms. The key normal forms are: first normal form, 1NF. This is a baseline requirement of the relational model. It dictates that all attribute values must be atomic, meaning they cannot be lists, sets, or other complex structures. Second normal form, 2NF. A relation must be in 1NF and must not have any partial dependencies. A partial dependency occurs when a non-key attribute depends on only a portion of a composite key rather than the entire key. 2NF is relevant only for relations with composite keys. Third normal form, 3NF. A relation must be in 2NF and must not have any transitive dependencies. A transitive dependency occurs when a non-key attribute's value is determined by another non-key attribute rather than directly by the key. For instance, if student ID to advisor ID and advisor ID to advisor office, then advisor office is transitively dependent on student ID. Boyce-Codd normal form, BCNF. This is a stronger version of 3NF. A relation is in BCNF if, for every significant functional dependency, x, y, the determinant, x, is a superkey. BCNF addresses certain rare anomalies not handled by 3NF. The standard method for achieving normalization is lossless join decomposition, where a problematic relation is broken down into smaller, well-structured relations. These smaller relations can later be joined back together to reconstruct the original information without any loss. An alternative approach, synthesis, constructs a 3NF scheme directly from a given set of FDs. The chapter concludes that achieving BCNF is ideal, but it's not always possible while also preserving all dependencies. In such practical scenarios, 3NF is often an acceptable compromise. Chapter 7: Multivalued Dependencies, Join Dependencies, and Further Normal Forms. This chapter extends dependency theory beyond functional dependencies, FDs, introducing more advanced constraints that capture other sources of data redundancy. These new dependencies allow for lossless decompositions of data even when no FDs are being violated. The chapter covers the following key concepts. Multivalued dependency, MVD. An MVD, denoted X double-side Y, describes a situation where, for a given value of attribute set X, the set of corresponding Y values is completely independent of the values of all other attributes. For example, if a course has a fixed list of required textbooks and a fixed list of instructors, but there is no connection between a specific instructor and a specific textbook, then the MVD course double-side textbook would hold. In MVD, X double-side Y is a formal statement that the relation can be losslessly decomposed into two simpler relations. Fourth normal form, 4NF. This normal form is designed to address the redundancy caused by MVDs. A relation is in 4NF if, for every non-trivial MVD X double-side Y, X must be a superkey. A relation in 4NF is automatically in BCNF. Join dependency, JD. JDs are a generalization of MVDs. A join dependency, written as star R1, R2, ... P, asserts that a relation can be losslessly decomposed into 3 or more smaller relations. MVDs are just a special case of JDs where the decomposition is into 2 relations. Project join normal form, or fifth normal form. This is the highest level of normal form concerning decomposition. A relation is in PJNF if every join dependency it satisfies is either trivial or is directly implied by its candidate keys. A relation in PJNF is guaranteed to be free of all redundancy that can be removed by decomposition. In conclusion, this chapter demonstrates that a well-designed database must account for more than just functional dependencies. MVDs and JDs represent more complex structural rules, and their corresponding normal forms for NF and PJNF provide the theoretical framework for creating database designs that are completely free of decomposition-related data redundancy. Chapter 8: Project Join Mappings, Tableaux, and the Chase. This chapter introduces a powerful and intuitive set of formal tools for analyzing and reasoning about data dependencies, with a special focus on join dependencies, JDs. The core concepts are: Project Join Mapping. This is a formal function that captures the process of decomposing a relation and joining it back together. For a given database design, a set of relation schemes, the mapping takes a relation, projects it onto each of the schemes in the design, and then joins all the resulting pieces. A relation satisfies the corresponding join dependency if this process returns the original relation perfectly. Tableau. A tableau is a visual, grid-based tool used to represent queries and dependencies. Instead of actual data, a tableau is filled with variables. There are 2 kinds of variables: distinguished variables, which typically represent the desired output or conclusion, and non-distinguished variables, which act as placeholders for any value. A join dependency can be elegantly represented by a tableau that has 1 row for each relation scheme involved in the join. The Chase. This is an algorithm that systematically applies a set of dependency rules to a tableau to infer new information. It operates like a logical deduction engine. When a functional dependency rule is applied, it forces variables in different rows to become equal. When a join dependency rule is applied, it allows for the creation of a new row by combining information from existing rows. The central conclusion of this chapter is that the Chase algorithm provides a universal method for testing dependency implication. To determine if a set of dependencies C logically implies another dependency C, one simply creates the tableau for C and applies the Chase process using the rules from C. If the Chase successfully generates a specific target, like a particular row for a JD or equating 2 key variables for an FD, then the implication is proven to be true. This provides a single, unified framework for solving complex dependency problems. Chapter 9: Representation Theory. This chapter delves into the theoretical question of what it means for a database, which consists of multiple relations, to be an adequate representation of a single, unified real-world concept. It formalizes and compares several different definitions of adequacy, moving beyond the simple idea of lossless joins. The primary notions of adequate representation discussed are: independent components. This is the most basic level of adequacy. It requires a one-to-one correspondence between valid database states and the real-world instances they represent. This ensures that each valid database state represents one and only one real-world situation, but it does not require that the join of the relations perfectly reconstructs that situation. Join condition. This is a stricter requirement. It mandates not only a unique representation, but also that the result of joining the relations in any valid database state must itself be a valid real-world instance. This condition implies the lossless join property. Information preservation. This is the strongest condition. It requires unique representation and adds the strict rule that no valid database state could possibly have been derived from an invalid real-world instance. This effectively means that checking constraints on the individual database relations is sufficient to guarantee the integrity of the entire conceptual whole. The chapter's main conclusion is that these conditions form a hierarchy of strictness. Information preservation implies the join condition, which in turn implies the independent components condition. A significant finding is that if the database constraints are limited to only functional dependencies, FDs, then all three of these powerful notions of adequacy become equivalent. The chapter also introduces the idea of data equivalence, a weaker form of equivalence between two different database designs, which holds if they can both losslessly represent the exact same set of instances. Chapter 10. Query Systems. This chapter provides a comparative analysis of the different formal systems, or query languages, that are used to express questions and retrieve data from relational databases. It evaluates them based on their structure and their expressive power, using relational algebra as the gold standard for a complete query system. The chapter examines 4 key systems. Relational algebra. This is a procedural system. A query is constructed as a step-by-step sequence of operations like select, project, and join. It explicitly defines how to get the answer. Tuple relational calculus. This is a declarative system based on predicate logic. Instead of steps, a user specifies the properties of the desired data. It uses variables that represent entire rows, tuples. It defines what the answer should be, not how to compute it. Domain relational calculus. This is also a declarative system, but its variables represent individual values from attribute domains, not whole tuples. This system forms the theoretical basis for graphical languages like QBE. Tableaux queries. This is a visual, two-dimensional query system where a user fills in a template table with variables and constants. It is intuitive and powerful for many common queries, but is less expressive than the full relational algebra. A crucial concept discussed is the need for safe expressions in calculus-based languages. An expression is safe if it is guaranteed to produce a finite result and avoid searching through infinite domains of values. The chapter's most important conclusion is that relational algebra, tuple calculus, and domain calculus are equally expressive. This equivalence is fundamental to modern database systems because it allows them to provide a user-friendly declarative query interface like SQL, which is based on tuple calculus, and then translate those high-level queries into an efficient, step-by-step procedural plan, an algebraic expression that a computer can execute. Chapter 11. Query Modification. This chapter explains the vital process of query modification or query optimization, which is how a database management system takes a query from a user and transforms it into an equivalent query that can be executed much more efficiently. This is a core function of any high-performance database. The key strategies for modification include translation into relational algebra. High-level, declarative queries written in languages like SQL are first translated into a procedural relational algebra expression, which serves as an initial, unoptimized execution plan. Algebraic optimization. This is the heart of the process. It involves applying a series of transformations to the algebraic expression to improve its performance. The most important strategies are pushing selections and projections. This is a powerful heuristic where filtering operations, selections, and column removal operations, projections, are performed as early as possible. Doing so dramatically reduces the size of the data being processed by later, more expensive operations like joins. Common sub-expression elimination. The system identifies parts of a query that are repeated, calculates them only once, and saves the result for reuse. Query decomposition. A strategy where a complex query involving many joins is broken down into a sequence of smaller, more manageable steps, often involving just one relation at a time. Tableau query optimization. For queries that can be represented as Tableau, the goal is to find an equivalent Tableau with the fewest possible rows. Since each row often corresponds to a join, this serves to minimize the number of joins in the final execution plan. Use of semi-joins. In distributed databases where data is spread across multiple physical locations, the semi-join operation is a critical optimization. It allows the system to reduce a table at one site to only the rows that will actually participate in a join with a table at another site, thereby minimizing the amount of data that needs to be sent over the network. In conclusion, query modification is a sophisticated, multi-level process that is essential for making database systems practical. It intelligently rewrites a user's request into a highly efficient plan by applying algebraic rules and considering the physical realities of data storage and distribution. Chapter 12: Null Values, Partial Information, and Database Semantics. This chapter addresses the complex challenges that arise when real-world information does not fit perfectly into the rigid structure of the relational model, specifically focusing on how to handle incomplete data and model complex semantics. The main topics and their conclusions are: handling null values. The chapter introduces the concept of a null value, represented by the symbol lambda, to signify data that is known to exist but whose value is unknown. This immediately complicates query evaluation, as simple true-false logic is no longer sufficient. It requires a three-valued logic, true, false, unknown, where a query is only considered definitively true if it holds for all possible substitutions of the nulls. Furthermore, the chapter shows that functional dependencies, FDs, can be used to logically deduce the values of some nulls. Marked nulls, e.g., %1, %2, are introduced as a mechanism to represent distinct unknown values that can be equated by the chase algorithm if dependencies demand it. Partial information and database semantics. The chapter moves beyond simple unknown values to address situations where a database represents multiple overlapping concepts rather than one single universal table. It critiques the universal instance assumption, UIA, and introduces the more flexible universal relation scheme assumption, which merely posits that an attribute name has a consistent meaning wherever it appears. Window functions. To navigate these complex semantics, the concept of a window function is presented. A window function is a formal mechanism that provides a single, consistent view or interpretation for any set of attributes by deriving a single relation for it based on the entire state of the database. This allows queries to be posed to the database as a unified whole, even if its underlying structure is complex and fragmented. In essence, this chapter concludes that dealing with the imperfections of real-world data requires significant extensions to the simple relational model. Handling nulls demands a more nuanced logic, while understanding the meaning of a complex database requires a formal semantic framework like that provided by window functions to ensure queries are interpreted consistently and unambiguously. Chapter 13: Acyclic database schemes. This chapter introduces and thoroughly analyzes acyclic database schemes, a special class of database designs that are structurally simple and possess numerous desirable properties that make them significantly more efficient and predictable than general or cyclic schemes. The main conclusion of the chapter is a powerful equivalence theorem. This theorem proves that for any connected database scheme, a whole set of different beneficial properties are, in fact, equivalent. If a scheme has any one of these properties, it has all of them and is therefore defined as acyclic. These equivalent properties include: 1. Acyclic hypergraph structure. The formal definition of acyclicity, where the database scheme, viewed as a hypergraph, contains no complex circular structures. 2. Gram reducibility. The ability to completely reduce the scheme's hypergraph to nothing by repeatedly applying simple elimination rules. This provides a direct, efficient algorithm for testing acyclicity. 3. Existence of a join tree. The relation schemes can be organized into a tree where, for any given attribute, all schemes containing that attribute form a single connected subtree. This structure guarantees an efficient, non-redundant path for joining all the relations. 4. Existence of a full reducer. There is a fixed semi-join program that can efficiently eliminate all tuples from all relations that will not participate in the final, complete join. This is a major advantage for query optimization, especially in distributed systems. 5. Pairwise consistency implies total consistency. PC implies TC. This property simplifies data integrity checking immensely. It guarantees that if every pair of relations in the database is consistent with each other, then the entire database is globally consistent. 6. The running intersection property. The schemes can be ordered in a sequence such that each new scheme's intersection with the combined previous schemes is fully contained within just one of the previous schemes. This allows for joins to be computed in a simple, incremental fashion. In summary, this chapter identifies acyclicity as a fundamental and highly desirable characteristic of database design. Acyclic schemes avoid many of the computational and semantic pitfalls of more complex designs, guaranteeing that queries can be processed efficiently and that data consistency can be maintained with simpler algorithms. Chapter 14. Assorted Topics. This chapter explores several advanced topics in relational database theory, pushing beyond the standard models to examine the deep connection between dependencies and logic, the limitations of those models, and potential extensions. The key topics and conclusions are: the connection between dependencies and logic. The chapter reveals a remarkable and precise equivalence. The rules for inferring functional dependencies, FDs, and multivalued dependencies are exactly parallel to the rules of implication in a fragment of propositional logic. This provides a powerful alternative framework for reasoning about these dependencies. However, a significant conclusion is that this elegant correspondence breaks down and does not extend to more complex constraints like join dependencies. More general dependencies. To address the limitations of JDs, the chapter introduces even more expressive constraints, such as template dependencies, TDs. TDs are a highly general way to specify rules about the tuples in a relation. The conclusion here is that while these dependencies are extremely powerful, they come with a major trade-off. For the most general cases, the problem of determining logical implication becomes undecidable, meaning no algorithm can solve it for all inputs. Limitations of relational algebra. This section proves a fundamental limitation of the standard relational algebra. It concludes that relational algebra, and by extension, the basic forms of tuple and domain calculus, cannot express recursive queries. The classic example is computing the transitive closure of a relation, such as finding all the direct and indirect managers of an employee. This requires a potentially unbounded number of join operations, which cannot be expressed in a single fixed algebraic expression. This theoretical limitation explains why practical query languages often include special extensions to handle recursion. Computed relations. Finally, the chapter considers an extension to the relational model to include computed relations. These are relations whose data is not physically stored but is generated on the fly by a procedure or function. This is useful for incorporating calculated values such as a flight's duration based on its departure and arrival times. The chapter concludes by defining the formal conditions under which a query involving such relations can be reliably evaluated. Chapter 15. Relational Query Languages. This chapter provides a practical survey of several major relational query languages, illustrating how the formal concepts of relational algebra and calculus, explored in previous chapters, have been implemented in real-world systems. The languages examined include ISBL, an early language that is a direct and faithful implementation of relational algebra. It uses symbolic operators like star for join and percent for projection, making its structure very procedural. Quell, the query language for the influential INGRS database system. Its range of retrieve, where syntax makes it a clear implementation of tuple relational calculus. SQL, structured query language. Originally developed for IBM's System R, SQL has become the industry standard. Its select, from, where block structure is based on tuple relational calculus, providing a powerful and declarative interface for users. QBE, query by example. A unique graphical language where users formulate queries by filling in example values and variables into on-screen skeletons of tables. Its design is a direct application of domain relational calculus and the Tableaux query concept. Peak, an experimental language that also uses a calculus-like syntax but is designed to operate over a universal relation interface. This means it automatically infers the necessary joins between tables, freeing the user from having to specify them. The chapter concludes that while all these languages are founded on the formal models, they invariably extend them to include practical features essential for real-world use. These common extensions include aggregate functions like count, sum, sorting of results, arithmetic calculations, and the ability to define virtual relations or views. A key takeaway is that most successful languages, like SQL and Quell, are declarative and based on relational calculus, as this allows users to specify what data they want, leaving the system's query optimizer to figure out the most efficient how.